Hi. So far in this, so far the last few videos, what we've talked about is we've defined speed. We've defined speed as the distance something moves over divided by the time it takes to move that distance. So in other words, the rate of how far it's going per unit of time. We have talked about the difference between speed and velocity. Speed is distance divided by time, whereas velocity is displacement divided by time. And those distinctions are important, but there's another distinction we have to talk about. And so I'm going to keep referring to speed here, but just please remember that velocity is a slightly different measure that measures something similar to speed, but not quite the same thing. Right now we're going to talk about the difference between average speed and instantaneous speed. I want you to think of a car speedometer. What does it tell you? Does it tell you the average speed that you're going over some time period, or does it tell you your speed right now? Because so far, all we've really talked about is how to calculate an average speed. When you use the equation v with a little hat over it equals d over t, you're finding an average speed. That's what that line over the v means. It means average. You're finding the average speed over some time period. You're not finding the speed at one instant, but that's what a car speedometer tells you. It tells you an instantaneous speed. That's what a car speedometer tells. It's instantaneous speed. Whereas when we first started talking about speed, we developed this idea of speed by first making a graph of distance versus time, drawing a best fit line, finding the slope, and then we realized the slope was actually telling us the average speed. So the slope of a best fit line of a distance versus time graph tells us the average speed of an object. A car speedometer tells us the instantaneous speed. Both of these are useful quantities, but they are different. So now we really have to define them and practice how, okay, well, how do we figure out what an instantaneous speed is? When might we need to find an average speed over an instantaneous speed? The definition of instantaneous speed is the speed an object has at a single moment in time. I'm not going to talk about how to find it just yet, but I will show you the examples where this is useful. We've already got one, a car speedometer. Tells you how fast you're going right now. Think about it. If a car speedometer told you your average speed, cars most of the time are parked in the garage or in the driveway. So the average speed would be really close to zero. That obviously isn't important information for you, especially if you're on the highway and going like 60 miles per hour or faster. So that's not really useful to you if it would tell you an average speed. However, if it tells you your speed right now, then you know if you're driving at a safe rate. So a car speedometer, that's an instantaneous speed. If you ever see like maximum speed listings, like the max speed of a cheetah or the max speed of a car or some sort of fish or bird, those are all instantaneous speeds. That doesn't mean that's the average speed that the object moves at. It means it's the instantaneous maximum, the very fastest it can move. Radar guns, whether you're talking about a radar gun in a police car or like a radar gun if you're measuring like how fast a baseball is thrown or a soccer ball is kicked or a volleyball is spiked or a golf ball is struck, those all measure instantaneous speeds, the speed at one instant in time. Basically, again, anytime you're trying to find the speed at any one instant, that's an instantaneous speed. Average speed, on the other hand, is, and we've kind of defined this already, the mean, remember mean is just a synonym for average, rate of change of distance over a period of time. And remember, distance is just a measure of how far an object moves. So as an object is moving, you take how far it has moved, you divide it by the amount of time it took the object to move that far, you've got the average speed. You find it by, first of all, one of the ways to find it is you make a graph of distance versus time, and then you take the slope of the best fit line of that graph. Slope of the best fit line of a d versus t graph over some section of data. that's the first and probably the best way to find the average speed. There is another way, which we developed slightly after we did the graph method. You can also use an equation, which it really boils down to literally the same thing. Average speed equals distance over time. V hat equals d over t. Okay? These will give you the same answer. However, if you have a graph, this first one is a little bit better to use. So if given a graph, first method is better. Usually just a little bit more accurate. It's a little bit easier to be accurate with it. Okay? And where is this useful? It's useful when we are dealing with any sort of large extended motion. So calculating distances or times or speeds for any large motion. Calculating your speed over the course of a race, etc. Okay, so we find average speed by either making a graph of distance versus time, finding the slope of the best fit line, or if we're just given numbers, we could use this equation. Average speed equals distance over time. If you think about it, that's literally doing the same thing as finding the slope. When you're finding the slope, you're finding change in y over change in x, so you're finding essentially the change in where the object is, the distance over time. And this equation is distance over time. Let's go back here. How do we find the instantaneous speed? There's a certain method that we're going to use, and it is known as the midpoint method. It's actually impossible to find an exact instantaneous speed, but we've got a really good way to approximate it. Here's what you do. To find the speed at some point, you simply find, and I'm putting quotes, even though it doesn't really need to be quotes, the slope using the two adjacent data points. So you're not finding the slope of a full best fit line. Instead, if you want to know the instantaneous speed at one point, you look at the data point before it, and you look at the data point after it, and you imagine finding the slope of a straight line between those 2 points. I can write it mathematically like this. If you want to find the instantaneous speed at, let's say, point 2 of a data set, you're going to take the distance for point 3, the point after it, subtract from that the distance from point 1, and divide that by the difference between time 3 and time 1. These are just subscripts. They're not coefficients. You don't multiply them or anything. Those are just labels for which distance, which time, which velocity we're talking about. All this stuff will make more sense when we actually start doing the math. So, measuring average and instantaneous speed on a graph. First thing we're going to do, it says to draw a best fit line for the graph and write the equation for this line. This is easy because all this data I designed to be exactly linear. So the best fit line usually would not do this, but it actually goes through every single data point, like so. There's a best fit line. We want to write the equation for this line. We know that the equation of a straight line is always y equals mx plus b, m being the slope, b being the y-intercept. This y-intercept, where it hits the y-axis, is 0, so we're not even going to have to worry about that. I just have to find the slope. Y equals something times x. In order to find the slope, I'm going to do this. I need to take 2 points that are on my line. I'm going to pick, since all the data points are on the line, I'm just going to use those. I'm going to pick this point right here and this point right here. And I'm picking those because those are data points that are easy to read both time and distance. This first one is at 5 seconds and 3 meters. The second one is 10 seconds and 6 meters. So when I go and do the slope, I'm going to do, again, let's see, change in y over change in x. So the difference between the y values, 6 meters and 3 meters. 6 meters minus 3 meters over the difference between the x values, 10 seconds minus 5 seconds. 6 minus 3 is 3, divided by 10 minus 5 is 5. You get 0.6, and the units are meters over seconds, or meters per second. 0.6 meters per second times x. That whole thing, 0.6 meters per second, that's the slope. And since this is a distance versus time graph, that slope is the average speed. So I'm just going to emphasize that right here. This is v hat. The average speed is 0.6 meters per second. I guess I could have written that down here as well. Okay, that's what you know how to do so far. What we're going to do now is we're going to find the instantaneous speed at two different points. Up a little bit. Okay, so we're going to find not the average speed over the entire interval, but the instantaneous speed at 2 points. So here are the points I'm going to pick. I want to find the instantaneous speed at a time of 2 seconds and at a time of 7 seconds. Okay, so here's 2 seconds and here's 7 seconds. The midpoint method formula says that in order to find the instantaneous speed, I need to look at the data around it. I don't actually need to look at the data at 2 seconds. I need to look at the data points on either side. So what I'm going to do then, for 2 seconds, I'm going to write it like this. The speed at 2 seconds, instantaneous speed, is equal to the distance for the data point after. I'm going to label that d3 minus d1 over t3 minus t1. Now the times are easy to fill in. T3 is 3 seconds, T1 is 1 second. The distances are a little trickier. If you look here, and I'm sorry these lines are so faint, this data point is at 1.8 meters, this data point is at 0.6 meters. So I'm going to write 1.8 meters minus 0.6 meters. 1.8 minus 0.6 is 1.2. 3 minus 1 is 2. The instantaneous speed at 2 seconds is 0.6 meters per second. Interesting. Let's see what it is at 7 seconds. This time, I'm finding the speed at 7 seconds, so I'm going to label V7. And you don't have to do the subscript, but I think it helps to understand exactly what you're doing. D8 minus D6 over T8 minus T6. And again, these are not numbers like you're going to do math with. They're just subscripts. They just are explaining which data point you're looking at. D8, that looks like it's at about 4.8 meters. D6, that's about 3.6. And the times are 8 seconds minus 6 seconds. 4.8 minus 3.6 is again 1.2. Divide that by 8 minus 6, which is 2. And you again get 0.6 meters. So that's kind of interesting. We found that there's the same instantaneous speed for each data point. And that would actually be true no matter which data point you looked at. And the instantaneous speeds are equal to the average speed. This is not a coincidence. I designed it specifically to do this, okay? This is a very special case. We see that we have a constant slope. Since the slope is the average speed, that means that our average speed is constant. Matter of fact, since the slope doesn't change, that just tells us that our speed overall is always constant for this particular graph because the slope doesn't change. The slope tells us the speed. If the slope doesn't change, then the speed doesn't change. So, for a constant, in other words, unchanging, slope, the average speed equals the instantaneous speed. So if your speed doesn't change, then your average must be equal to the instantaneous speed. And that makes sense. Think of it in terms of like test averages or something. If you always get a score of 100 or on a test, then that means your average is 100, but also each individual assignment is also a 100. Okay? Each individual assignment is kind of like your instantaneous speed. Your overall average is like your average speed. This only happens if you have perfectly spaced data like this, where the distance goes up by the exact same amount each time. That's a constant average speed. The object is moving at a constant speed, it's not varying at all, and in that case, the average speed is equal to the instantaneous speed. However, that is not always going to be the case. If you look at this next example, you can see already that not all this data can be connected by a straight line. This slope right here would be a little shallower, this would be a little steeper. We're still going to draw in a best fit line though, because it's pretty constant data. I think your best fit line probably looks something, about like this. Oh, didn't mean to do that. More or less like that. And we can also find the, equation of the best fit line here again. I'm going to say that this, let's see here, I'm going to take this data point right about here. And again, your line will look a little different, so your answers would be just a little different than mine. And this data point right here. And notice that I actually didn't circle data points. Right here I'm circling right below this data point, and right here I'm circling to the left. I'm looking for places where it's going to be really easy to read the data. Okay, that's what I'm trying to do here. You don't have to, when you're finding the slope of a best fit line, use the actual data points. You use whatever is easiest for you to read. We know that the slope is equal to the average velocity. And since we're looking for the average velocity, we're going to take the difference between the distances here and here, divide that by the difference between the times here and here. Okay, so at this point right here, we've got 4 seconds. This point right here, I designed this to be at about 2.4 seconds, so that takes care of the times. 4 seconds minus 2.4 seconds. Up top, the distances, this one looks to be at about 8. This one is at about 6. 8 meters minus 6 meters. Okay, so the difference in distance, 8 and 6, minus over the difference in times, 4 and 2.4. 8 minus 6 is 2. Divided by 4 minus 2.4 is 1.6. 2 divided by 1.6 gives us 1.25 meters per second. So the equation of this best fit line, remember, best fit line, the slope of it is telling us the average speed. Y equals, here comes the slope, 1.25 meters per second times x plus the y-intercept. This y-intercept, where the best fit line crosses the y-axis, is not 0. Looks like it's at about 3 or so. So plus 3 meters. Because the y-intercept is in meters. It's where it crosses the y-axis. Y-axis has units of meters. So we've got a best fit line. We're saying the average speed of this object that we took this data for is 1.25 meters per second. Now we're asked to calculate the instantaneous speed at 0.5 seconds and 3 seconds. Let's do the first one. At t equals 0.5 seconds, we would do this. We're going to look at this data here. I'm not going to write it like that. So this is the data point we want to know the instantaneous speed at. We need to look at this data and this data. Clearly, the times are easy. 1 second minus 0 seconds. The distances are a little trickier to read. This one is just under 4. It's actually at 3.8 meters. This one is a little bit farther down. Remember, I don't use this data. It's at 3.4 meters. So, 3.8 minus 3.4 divided by, I guess that would be 1, would be 0.4 meters per second. And that's interesting. 0.4 is the instantaneous speed right here. It's the speed during this interval. And again, I don't think I really alluded or talked about this earlier. This is an approximation. It's actually impossible to find an exact instantaneous speed, but by taking the time interval between the two data points around the point at which you want to know the speed, you're reducing that time interval so that's like really small. And you could imagine taking more and more data so that the distance between, the time between your data points is smaller and smaller and smaller. If it gets infinitely small, which obviously can't really happen, but you can approach it, that would be like an instantaneous speed. Basically the speed right at this instant, how far did this object travel in 1 instant? Okay? So even though we can't actually find a perfect instantaneous speed, we can approximate it by taking the basically the average speed, because this formula is the same as the formula for average speed, over a very small time interval. In this case, 1 second. So we notice that this instantaneous speed is 0.4 meters per second. It's much lower than the average speed over the entire interval. And that makes sense because if you look at the slope for these 3 points right here, these first 3, it's much lower. The slope of an imaginary line between that data point and that data point, it's much lower than the best fit line that you drew. It's not as big of a slope. What about at 3 seconds? Okay, there's 3 seconds. So we need this data point and this data point. This data point, the time is 3.5 seconds, minus the time over here is 2.5 seconds. So again, a gap of 1 second. This data point is actually just below 8. It's at 7.8 meters. This data point is just above 6. It's at 6.2 meters. 7.8 minus 6.2 is 1.6. Divided by 1 is still 1.6 meters per second. Now notice that the instantaneous speed has changed. It's now higher. It's actually higher than the average slope, which makes sense if you look at it, because if I connect all these points with the protractor, the straight line on the protractor, you can see that that's a steeper slope than the actual slope of the best fit line. Okay, so we see that when the slope of the data points themselves, the data points don't have slopes, but like the general trend, when the slope of the general trend of the data points increases or changes in general, that means that the speed is changing. Okay? I'm not talking about the slope of the best fit line. That itself doesn't change, but we drew that in. You can tell that the trend of these data points, if you were imagining to like draw a whole bunch of different slopes just connecting each point, the slopes get steeper as you connect, as you go from here to here. Okay, if you're actually connecting the points, and we never ever connect the points in this class. But if we did, you can imagine that the slope of the trend illustrated by the data would change, and it gets steeper in this case. What that means, if the slope gets steeper, the value of the slope gets bigger, that means that the speed is getting bigger. So a changing slope of a d versus t graph means that the speed is changing. Now, in real life, you're probably not going to have data like the first set. You're probably not going to have data like the second set. You're going to have real life data that looks like this. It's more of a jumbled mess. But this is actually really good data. If I were to draw a best fit line through this data, it would look more or less like this. Okay? It would look more or less like that. If I want to find the equation for the best fit line, the y-intercept appears to be at, I don't know, 0.75 meters. We just have to find the slope. I'm going to say that the slope, let's see here, let's find somewhere easy to do this. We know that the slope of the best fit line is equal to the average speed. And let's see here, where's a good place that this crosses? I'm going to say right about there. That's 2 seconds and 1, 2, look about 1.2. Okay, so 1.2, so 2 seconds and 1.2 meters. Let's find another good one where it's nice and easy to read. That looks pretty good. And that's at approximately let's see. I'm horrible at reading. I should have numbered this better. That's at about 2.8 meters. So I have 2.8 meters minus 1.2 meters. That was at 9 seconds. This was at 2 seconds. So 2.8 minus 1.2. 1.6 divided by 7, I get 0.2285, etc. I'm going to do 0.23 meters per second. That is my average speed because that's the slope. That's the average speed this object was moving at. But obviously, if you look at the kind of jagged pattern, this object is moving different distances each second, okay? Moves a lot here, then not as much, not as much, a little bit more, not as much, a little bit more, a little bit more. And you'll notice I'm getting that by just looking at how much it moves up in distance. All these points are separated by the same amount in time, but not in distance. So there's an average speed, okay? It's not always moving this fast. What we're going to do now is find the instantaneous speeds for each possible point and fill out the table. So we're going to find the speed at 1 second, 2 seconds, 3 seconds, 4 seconds. If it says seconds up here, you don't have to write it, so I don't know why I was doing that. 5, 6, 7, 8, and 9. We're going to find the instantaneous speeds using the midpoint method. There is something interesting about the midpoint method. There's a limit to how it is used. Because the midpoint method is defined as you have to have a data point before and a data point after for it to work, you actually can't use the midpoint method to find the instantaneous speed at 1 second here or 9 seconds. At 1 second, there's no data point before. There's a best fit line, sure, but there's no data point. Same thing at 9, except now there's no point afterwards. You don't make up a data point. You can't forge the data. Instead, you just say that you can't find, using the midpoint method, the instantaneous speed at 1 second. You can find it at 2, 3, 4, 5, 6, 7, 8 because those have data points before and after them. But for 1 second and 9 seconds, that's just a limit. You can't find the data for that. Okay? There's nothing else to do about it. You don't want to make up the data, so it's not a big deal. You still have 7 things that you can find the instantaneous speed for. So, again, just to demonstrate, at 2 seconds, I would find the instantaneous speed by looking at the data for 3 seconds and 1 second. At 3 seconds, the object that this data is representing is at 1.5 meters. At 1 second, it was still back at 0.8 meters. 3 seconds minus 1 second. 0.7 divided by the gap of 2 seconds, 0.35 meters per second. So what I'm going to do now is I'm going to find the rest of these data of these instantaneous speeds quietly. So I'm just going to do this real fast. So interestingly, what you see is the instantaneous speed is always changing, and that makes sense because you can see that the trend of the data is always changing. It's always going up, but by different amounts each time. So if you were to connect all these data points, you would see that the slope between each pair of data points is changing each time, and therefore the instantaneous speed is changing each time. Again, we never ever just connect data points. It's a big no-no. So the instantaneous speed is always changing, but notice it's always around 0.23 meters per second. It's always near the average speed, which makes sense, but it's never exactly the average speed, and it also changes a little bit. The reason that we find instantaneous speeds, other than just wanting to know what the speed of the object is approximately at any instant in time, is that this allows us to now generate new data to make a new graph. What we're going to start doing now is getting instantaneous speeds and then making a graph of how the speed looks versus time. We're now going to start making graphs of instantaneous speed versus time, and then we're going to analyze those graphs and see what information we can get. If you have any questions about what we've done today, please let me know. It's a pretty straightforward idea, average speed, instantaneous speed. To find instantaneous speeds, we use the midpoint method. You can't find the first or last data points, but other than that, it's just like a little mini slope calculation. Again, if you have any questions, please let me know, and I will talk to you at the next video.